Welcome to the Blitz Town Hall. In this town hall, we'll be going through the review classification puzzle, where you have to classify similar reviews together and predict their sentiment. In this puzzle, you'll learn how to build a text clustering model, generate text embeddings using BERT and k-means. And let's first go through what the puzzle is about. So over here, you're given an input text, and from one single input text, you have to output two different things. One is a review class, and another is a review sentiment. So the review class is not defined, but if you go through the test and validation data set, you might be able to pick up some hints over there. So there are three different categories, and you have to identify what category the input text falls into. You also have to identify whether the input text has a positive sentiment or a negative sentiment. We'll be building a text clustering model that reads an input review text from customers and clusters the review into three classes, along with predicting the sentiment of it. We will first start by exploring the data set in depth, and we'll be using the NLTK library for this. Jyot is going to be talking more in detail for that later on. We'll then move on to generating text embeddings for the entire review and using pre-trained model called Distilled Roberta from Hugging Face. And we'll also be using the sentence transformers library. So what are some of the applications and uses for this problem? By solving this problem, you'll learn how to prepare a text corpus for processing. You will also learn how to build intuition for clustering text in an unsupervised problem. And you can predict text sentiments. Now, this is not applicable only just for the input from this puzzle, but you can use these techniques for input text for any of the puzzles. These are standard natural language processing techniques and methods, and you'll be taking them forward for any other challenge that you choose to work for. So now I'll be asking Jyot to explain the beginner's baseline, followed by Nimish, who will be explaining the advanced baseline.
I hope it's visible. Okay,
yes.
So as you know, the problem is text clustering problem with unsupervised learning. So unsupervised learning is one of the machine learning approaches where we don't have the labels for any type of text like images or any types of data like text, images, or graphs. So in this problem, we will be using NLTK library, which stands for Natural Language Toolkit, and we will use another method, GLOW vectors, that is global vectors for word representation to extract word embeddings, and then we will perform two subtasks. The first one is review classification. We will be using text blob for that, and another one is clustering. We will be using extracted embeddings for that. Now the task is simple. We will start with data pre-processing. Data pre-processing is an essential step in any type of text. There is one old saying in computer science that is garbage in, garbage out, and this is also true for text data. Since our text data does not have uniform dimensions, it can be of 10 character length, it can be of 100 character length as well. So we will start with text data cleaning, which is text cleaning. Then we will go through NLTK utility functions to perform tokenization and stop word removal. These are the two main functions in text cleaning or pre-processing, which are required for any type of natural language processing task. A few other are stemming, lemmatization, and other few other like having extract embeddings from text or sentences. We will use we will use word embeddings using GLOW. GLOW is global vectors for word representation. It is trained on around 840 billion tokens, which is a lot. And we will go through it later on how we will do it. So starting with the setting up workspace, this is a standard method to download the data or set up the library. We will use AI crowd CLI function, which is just basically downloading the function and using magic function to download the data. You also need to log in here. using AI crowd login function. It will redirect you to our AI crowd homepage for authentication. One thing to notice here is that this review classification, this is keyword for each individual challenge or any puzzle. So we will put it here to download our data set. Now these are the functions or libraries that we will be using for our basic simple baseline. NLTK is an important NLP library since it provides a large variety of NLP functions, utility functions, as well as it can do some things like classification for some problems or semantic reasoning as well. It can provide parsing tree as well, but we are not going through the deep details into it. We will simply use a few functions like stop words, word tokenize, or quote estimator. Next is text block. Text block is also a Python library, and it has been used here for sentiment classification. So we will also import or download it here using pip. Both of these libraries are there. Now, these are the simple standard Python utility libraries for graph visualization or any standard tasks. The next thing is Stanford Glow. So this Glow is a vector embedding for word embeddings for uh, text extraction. Now to download it, we will have to download whole text zip. So the word embedding zip will be downloaded here, and the next step is to go through the data setup. So till now we have gone through setting up the workspace and importing the libraries. So our next thing is starting with the data set. The data set has been provided into in CSV format. We will be using pandas to read it, and as you can see, the data set is simply text sentences in each row. So our training data contains 200 training data contains around 200 rows or sentences, but later on we will see that how 200 can be used. Like this is simply text which is a bunch of words. It also contains some punctuations, some digits like this. So we will be going through data cleaning and data pre-processing to extract meaningful information from each sentence. This sentence can be meaningful to us, but to machine it is nothing more than just random bits, zeros and ones. But in order to convey the information or the each data, the meaning of each data, we have to convert this text into a numerical representation. And the first step is cleaning the data set, because the data set is raw and it contains many things. So the standard cleaning function is like this. We first convert the text to lowercase, then we will remove any white spaces or new links. We will also remove any redundant things such as hyperlinks, numbers, punctuations, and then finally we will join the clean text into this sentence. So what we get after cleaning this thing is all these punctuations and redundant things are removed from the text. Now we will get a simple sentence which is made up of a bunch of words. Now, the next important part in our end-to-end code baseline is data pre-processing. There are many methods to apply data pre-processing in text, but one of the two important of them are tokenization and stop words removal. Tokenization is a process of dividing the text of probably larger document, or even a sentence into smaller tokens such as words, character. There are many type of tokens such as multiple words, like n-gram character, n-gram words. N-gram character is like having n words, n characters together, like 2 character, 3 character. N-gram can be of different types, like bigram, where 2 words are coupled together to create one token. And here we are using simple word tokenized tokens, like each word represents one token from our data set. So we use this word tokenize function from NLTK library to perform this tokenization. And this is another utility function to like to visualize how our data set is pre-processed using this function. Like our data set format is a pandas data frame, so it is another simple function to uh, using this apply method and perform this tokenized text function. Next important thing in data pre-processing is stop word removal. Now, since in images we contain pixels for each individual tokens as a pixel, but here there are many tokens which are redundant to us, such as is, the. These words does not convey overall significant meaning to a sentence, but it also since we are using normal k-means clustering, that is unsupervised learning method, so it would not be significant here to take into account how this method affects the training time. But when you use larger models like Roberta or BERT, it will be of significant it will be of significant importance that these stop words are removed, because it will create our data set much denser, and it will remove any redundant information that is present in our data set. So to do that, the analytical library provides one list of English word stop words that are like and, me, the, which are not important in our context, but anyway, it will not be used to convey any meaningful information representation. So we will remove the stop words using this remove stop words function. And similarly, as we applied the first function, we will use data frame apply function to use this to remove stop words from here. And finally, we will stick together two of these functions, and we will create another function to apply whole pre-processing pipeline. Now, we after pre-processing and applying data cleaning, what we get is a simple collection of words which from which the stop words have been removed, and it does not contain any punctuations or any redundant information. So it is now an ideal text data set to work with. Now, since we got the data set as a bunch of collection of these words, we need to convert it in some to a into some numerical format, which will have from which we can get meaningful clusters. Like our first task is to create clusters from text, but since we can't use this text to directly cluster those together, we need to have some numerical representation from that. So to do that, we are using this glow function, and it for each word this is basically a dictionary of collection of a word and the corresponding numerical 100-dimensional vector. This glow vector, this glow, that is global vectors for word representation, is trained using unsupervised learning on 840 billion tokens, and and that is enough for our task, because this word embeddings will have meaningful representation. It is just that our text will not be readable or understandable to humans. Like for example, let's take four words: queen, king, man, woman. In this word embeddings, it is a higher dimensional representation of words. For example, this glow is of 100-dimensional vectors, and to visualize that, we can comprehend the 100-dimensional space. We will work with 3-dimensional space. So here, the king and queen will have similar distance as that of man and woman. So if you take one vector of man and then you subtract it from the vector of woman, you will get the difference between two vectors, man and woman, and then you will take the difference and add it to queen. You will get similar, you will get another vector which is very similar to king, because the vector space difference is the same as between these two words. And hence we can say that this word to vector glow, it it contains information in semantic similar information and syntactic similarities. So it is very useful in our case. Now to extract embeddings, we are using this text that we downloaded earlier, and we will create a dictionary from this important embeddings into corresponding keys which represent each word, and embeddings which represent individual keys. So here we will extract embeddings for each word. Now, since we already have a dictionary, and we already have a bunch of text, bunch of words. Now, there is only one problem, that is that we have bunch of collection of words or sentences in our input, but the word to this glow embeddings, it only takes individual word as an input. So to overcome that, one method is, okay, someone has questions. Okay, nobody has question. Please let me know if you have any questions. Now, to extract these embeddings, one method is to take individual word embeddings from each sentence. Then we will do an averaging over all these word embeddings, and the final uh, word final sentence embedding will be used to do clustering. So this is one of the method. Another method would be to take a mean mix from each word embedding shape and provide those as a final sentence embedding. Uh, yeah, since we already talked about this, word embedding is of 100 dimension. One method to visualize this is using t-SNE. It is a dimensionality reduction technique to visualize higher dimensional data. And here we are performing t-SNE to reduce the dimension of our word embeddings. And here are a list of few keywords or words from this glow embeddings, which you can see, like this monitor or memory or CPU. So we can see that those are clustered together compared to any other thing, any other words which are not from this computer science related thing. So let's move on to next part, which is text embedding generator. Now, since we already have method to extract sentence embeddings from text, we will apply this function, which basically uses this get function for to take embeddings from corresponding to each word. We will apply mean, that is average, to get final embedding, average embedding from that, and we perform this task on both training dataset as well as test dataset. So the finally the dimension we get is 100 dimension, because the word embedding is of 100 dimension. So now we have a vector representation for each sentence, and we want to cluster it together. So how can we do it? Because this task is an unsupervised learning task, one method is to perform k-means clustering. It is one of the very simple algorithm, but works really well for a large range of applications. And this k-means clustering algorithm works by iteratively. What it does is it creates n clusters or k clusters given input dimensions, like this word embedding or any type of data which is of uniform shape or higher dimensional representation of any corresponding data, even images. So this k-means clustering will perform clustering on higher dimensional data, and it will output n clusters or k clusters given those data. Now, how it does is uh, it will first take n random higher dimensional points. Then it will iteratively go through each of those points. It will measure the distance between all those initial cluster means, or which also known as uh, k mean, because we have k number of points and it will take mean of all of them, yeah, mean of all those points in the next step. So basically in the first iteration we will have k points selected randomly as means. Then for each individual point in our data set, it will take the distance, and it will assign each individual point to its nearest cluster mean. In the next step, it will find a mean of that selected cluster. So now we have a new mean, and again we will perform this distance measuring and assigning for each point, and it will iteratively converge to cluster mean. So in this example, since we already know that in our this problem we have 3 review classes, so we can select that our k-mean clusters algorithm will output 3 clusters, and we also know that this n clusters, which is one of the parameter in k-means sklearn library, it will output 3 clusters. So we will have value of 3 here for so this is the first model, unsupervised learning model, that we will use to classify each review classes. Another thing that we want to predict is sentiment, and to do that we will use this text block function or library to perform this sentiment classification. So basically it will output 1 if the polarity is greater than 0. It will return 0 if it's 0 or negative. So finally we have 2 methods that will solve each of our subtasks, and putting it together we will fit our model on this k-means clustering algorithm such that it converges to 3 clusters. Now we have done the training, or training in case of this clustering k-means. We will do evaluation for our model or our data set. So to do that, we use this predict function from this sklearn library k-means model, which we already trained. So here we will get the final review class for each test input, and sentiment for each our text input, but it will use this text block to output the sentiment prediction. The next step would be to visualize the our prediction, or a higher lower dimensional representation of our prediction using this PCA or tsnm. Now the output looks like this, but since we have 3 clusters and our data looks like kind of 2 cluster, but it also really well, it also divides the data really well, since these 2 cluster cluster 1 and 2 are patched together, but it looks like the model has predicted correctly. And finally, similarly, the sentiment representation is also well formed. Like this part is correspond to class 1, this class correspond to class 2, and we have prediction for our test set. Now, the only thing that is remaining is to do your first submission. Now we can do that by already taking our data set predictions, and corresponding to each class we will do this we will apply this function like to these predictions to our data set. And for corresponding each text or row, we will have one class that is a review and sentiment for from 0 to 1, 0 and 1, and we will apply our predictions to this data frame. Finally, we will use AI crowd function, notebook submit function, to submit our predictions to the website. So, this is your first step in creating an unsupervised learning model or for text classification. There are many other methods you can use, such as trying advanced methods such as BERT, which Nimish will explain in a while. You can also use sklearn unsupervised model to do voting classifier or different methods. So here are the next few things you can try: Hugging Face sentiment classifier or transformer libraries. Now I will hand over the task to Sneha Beg. Now I'm stop sharing the screen. If you have any questions, let me know.
Thank you, Jyoth, for that explanation. Now I'll invite Nimish to explain the advanced methods, including BERT and SQL. Nimish, we can't hear you in case you're speaking.
Oh, sorry, just fixed it. Are you guys able to hear me now?
Yes, yes.
Okay, great. I'm just sharing my screen. So can you confirm if this is legible?
Yes, your screen is visible.
Okay, great. So, the beginner baseline was more or less to give you context on like the entire challenge in and of itself, like what the data set looks like and what traditional approaches like you could use, like simplistic approaches, to just get an understanding of how more complex approaches work. Because the approaches that I'm going to be describing in this notebook are more or less similar to what Jyoth just explained, except the pre-trained models that we use are just better. I'll show you proof of that when we get to it. So the goal of this notebook is to I say this is advanced, but in reality, this is going to be a shorter notebook because a bunch of libraries are going to be doing most of the heavy lifting for us. And by heavy lifting, I mean more or less the processes or the steps that you were doing in the simple notebook will more or less be taken care of by the libraries over here. So this notebook is more or less meant to introduce you to the existence of these libraries and how you can use them in your own projects, not limited to just classification for texts, but it could be anything as well. So I will be skipping the initial part of the notebook, which is essentially setting up the workspace, and everything else works the same. And the same usage of loading in the data frame and all that things. So now the first place we stop is actually just looking at what the words, filtering stop words out of the sentences. And it's important to note here that we won't be needing to do any of the pre-processing for the approach that I'm going to describe, because like I said, they will take care of it for themselves. But in this case, if you in a simple way, if you wanted to prune stop words out of your corpus for any purpose, you could just so stop words being the submodel from NLTK. After you download the English version of the stop words, it contains essentially a list of stop words that are common in the English language. And your job would then be to actually just save those words from your sentences, which are not present in the stop words list. So that's as simple as it gets for ways to prune out the stop words from your sentences. But proceeding to actual meat of the notebook, or like the actual place where we have something new to learn is, so we will be using something called Distill Roberta for actually extracting the embeddings out of sentences. And it's important to note the word sentences here. So we will not be extracting embeddings from individual words like we did with the previous notebook. So Distill Roberta actually supports, you can pass it a single sentence and it will return a 768 dimension vector representing the sentence in some latent space that is a complete black box to us. Like we won't know what is happening inside it. But yeah, that's where I give you a little bit of context on the Roberta model. So Hugging Face trained this model called Roberta, which is a large model that was trained on multiple data sets of the English language, like large corpuses. And it was trained a little bit differently than how you would train traditional RNNs, as in the way that traditional RNNs would try to understand what the syntax and semantics of the English or any language for that matter would be, is it would try to predict the next word in a sequence of words to try and get a better understanding of what the language is. However, when they trained the Roberta model, what they did instead was, instead of trying to predict the next words, they would pass it a sentence and they would mask certain bits of those sentence. And the job of the model here would be to predict the missing pieces of the sentence. And people have found that this way you actually get a much better, the model gets a much better understanding of the English language. And so since this model has been pre-trained on that, we can take those parameters, download it exactly as it is, and we can edit it to perform custom tasks. And those custom tasks could be anything, beginning with the sentences as the starting point, the vector representations as like the intermediate point, and then we could pass it on to whatever we want to do. So that's exactly what we'll be doing here. So we'll be using the trained model, all still Roberta we want. So all is just, you can find this in the documentation. All just stands for one of these models, which is suitable for, it's pretty generic and it's suitable for most use cases. You could use it for classification or even sequence prediction. So it could be suitable for most things. If you wanted something more specific, the documentation will help you find things. So this is why I introduced the first module that we'll be looking at today, which is a sentence transformers module. So this module contains a large number of pre-trained models. And in this case, we are using it for extracting embeddings out of sentences, although they support extracting embeddings from images and other bunch of stuff. So if you look at the actual documentation, they'll have a list of usages, which they support in the module. And yeah, it's pretty useful for reducing or transforming the dimension, you could say, of certain data to, let's say in this case, text to numerical vectors. So we will be instantiating the transformer with the model that we chose, and we'll be calling that the Distal Roberta sentence encoder, because the whole purpose of this model will be not to train or anything. We'll just be using the pre-trained model to extract embeddings out of it. And the second thing that we'll be looking at is transformers, specifically the pipeline class of transformers. So what this takes in is, so the way that transformers works by Hugging Face is, their concept is pretty straightforward. So they have a list of tasks that they can solve, and they have a bunch of models for each task. So your job is to pass in a particular task. If you pass it a particular task, it will take the default model for the task, or you could be more explicit and pass a model for the task yourself. So taking in just these two things, it returns a callable function that you can pass in with whatever is meant for that task. So in this case, for sentiment analysis, you're expected to pass it a particular text. There are other tasks as well that support similar operations for images and so on. So the pipeline submodel is meant to be really versatile and kind of used in any place, just a drag and drop replacement for most common ML tasks. And it's important to note that they also perform really, really well compared to training one yourself. So in most cases, you really don't have to train anything yourself. You could use the pre-trained models present for a particular task and instantiate them with the pipeline, and it returns a callable. So in this case, what happens is you pass in a text to the callable, and it returns an object with a key called label in this. And since the task is specifically sentiment analysis, the label can take two values. It could be either positive or negative. So we're just writing an abstracted function out of it. So we pass it a text and returns 1 if it's positive and 0 if it's negative. Pretty similar to what we saw in the earlier notebook, except this case, it makes use of the pipeline by transformers. And so to actually encode a bunch of sentences, what you would do is call the model dot encode on a list of sentences. And since the list of sentences are in the data frame, it doesn't really matter if it's a data frame column or a list of sentences or array of something else. It really doesn't matter. It will take that entire list and convert it to embeddings. So what's really important to note here is that these are not words or individual tokens, but these are full sentences that have been encoded to high dimensional representation. That again is a black box to us. We don't know what each of the dimensions kind of signify. But all we need to know is that they have been encoded, and the pre-trained model works great for most tasks. So they have been encoded in a latent space such that the syntax and the semantics of specifically English language in this case are preserved in those sentences. So then the task becomes pretty straightforward. We will be using those embeddings to train the k-means clustering algorithm. So again, k-means, like my colleague explained earlier, is a pretty simple unsupervised learning technique. It's pretty simple. At the same time, it's pretty powerful. And this is where a lot of domain expertise or experience can come helpful. So k-means expects one particular argument to be filled by the user, which is n clusters. And why I say domain expertise is necessary is because in this puzzle, we know for a fact that there are 3 classes. So it's easy for us to fill in 3. When you're doing data exploration in the real world, chances are you really don't know what to expect, how many classes are there. Except if you had some amount of domain expertise with the data you're working in, you could make a ballpark guess of how many classes there are. And you could try the class -1, class +1, and the number of classes itself, and see which one gives the best segregation and the best scores for the data set. So that's what you would be doing in the real world. In this case, we know for a fact that there are 3 classes. So we will be instantiating a clustering model with 3 classes in it. And how it works is it picks 3 random points within the data space, and it computes all the points that are closest to that one of those random points. And so whichever point, for every single point, the distance to the centers, in this case, the 3 points are computed, and they are associated with the center that they are closest to. And once that is done, the centers are recomputed to all the data points that were associated with that center. And this keeps repeating until it converges, or the centers don't shift, as in the centers, the points for the centers. In this case, it's 2-dimensional, and these centers are decided and they don't change, or they alternate between 2 points, which also shows it's a proof of convergence. So fitting our entire data on that, it's going to learn the inherent patterns in the data set itself, and come up with 3 different centers that work best for the embeddings. And when it's time to predict, so what you would call is same as we did in the earlier notebook. You would call the dot predict method of the model, the trained model, on the test embeddings. And this time it would basically classify them into one of the 3 centers and return an integer, which is what will be contained in this array. The list. It's essentially a list of integers from 0 to 2, 0, 1, or 2. And similarly, we will be applying the predict sentiment Roberta function. If you recall, it's the function that we wrote earlier that can take in a text and returns 1 or 0, depending on if it's positive or negative. So what dot apply of a particular column. So this is the data frame, test data frame. So the reviews column, dot apply. So what dot apply does is you pass it a function, and it applies that function to every single row in the data frame. And we return the values because it returns it returns a NumPy array. And so what this would save is essentially, again, a list of 500 elements in this case, because there are 500 test samples, and each of those integers are 0 or 1 for their classes. So, and again, we want to visualize this. So what the embeddings look like. And again, there are 768 dimensions, way too much for us to comprehend or visualize in a very efficient way. So the best way to do that would be to use t-SNE, like my colleague described earlier. And what I want to add to what he explained is that t-SNE is very efficient at reducing the dimensions to 2 or 3, specifically something that helps us visualize and interpret data. So one goal, or not one, like one of the many goals of dimensionality reduction techniques is to preserve the information and also make it easy for people to interpret it. At least that's that's the major use case of t-SNE, since you can reduce any arbitrary high dimension to 2 or 3 dimensions. It makes it easier for us to visualize it in a 2-dimensional or even a 3-dimensional graph. So you'll notice that these representations in lower dimensions look drastically different to what the previous approach showed us, and you'll also notice that these are pretty well clustered, as in their embeddings are pretty well clustered. So once because it's been reduced, and you can also assume that what we see here is approximately similar to what the information is even in a higher dimension, as in whatever is closer here would be closer even in higher dimension, whatever is further apart would still be further even in the higher dimensions. You can notice that these embeddings that were extracted out of the sentence transformer using the distal Roberta were really good at kind of classifying different sentences into different regions. They were really good at it to the point where you can distinguish yourself. So when you use a k-means clustering algorithm or some method to actually distinguish them, it's not going to have too hard of a time to actually draw boundaries between them. So in this case, the centers would be around here for the 0th class and here for the 1st class and around here for the 2nd class, approximately, taking a look at the data. So when the embeddings are good, the models can also converge faster and converge to better optimal solutions as well. So that's really important to have good embeddings or good representations of the data. And so this is what the representations look like for the 3 classes of reviews. And similarly, taking a look at the sentiments behind them, this is what they look like. So you can see that one of these classes, class 1, is dominated heavily by positive reviews, and the other class 0, is dominated heavily by negative reviews, and the other class 2, has an approximately equal number of positive and negative reviews. So it's really easy for us to gain insights like these when both the embeddings are great and the visualization technique also perform what it's designed to do so. And the next part will be pretty similar. We'll just be constructing a data frame out of the predictions, and we'll be making a submission to Aircraft. And yeah, so the goal of this notebook, like I said, was to introduce you to both transformers pipeline and also the pre-trained models of sentence transformers, which have other usages as well, because they are really useful in a variety of contexts. And for most part, you really don't have to construct models yourself, because these have been trained on so many tokens and have so many parameters that they usually perform really good out of the box, and they give state-of-the-art results. So does anyone have any questions?
I have a question.
Yes.
One question I have, or actually I have a few questions. So one question I have is for evaluation, you are using RAND index. So do you have a ground truth clustering of this data, or how do you actually compute RAND index?
Oh, yes. So obviously, we do have a ground truth of clustering because these were synthetically generated data. So we have the exact labels that were associated with the data.
I see. So what I was trying to do is, I'm not finished yet, but what I'm trying to do is to actually identify the cluster. So I did t-SNE and tried to basically map the points in 2D to the texts and to identify the clusters.
Okay.
To proceed, so to say, in like semi-supervised way. So I basically assign labels to some rows of data and then build a classifier, and I use also unlabeled data.
Okay.
So I'm just curious if the clusters that I identified are the right ones. Can you maybe share what the clusters are?
I will have to discuss that with the rest of the team and get back. It's not typical for us to share the actual results themselves, but maybe I can get back to you on that after discussing it with the rest of the team.
Okay, yeah, thank you.
Yeah. So from what I understand, you basically want to evaluate your approach and whether the classes that you identified yourself as like by yourself manually were the right classes, if I'm not wrong.
Yes, exactly.
Okay.
So if the direction of my labels is the right one.
Got it. Okay. I will discuss that and kind of get back to you on that. Because, it's not typical for us to share it, but yeah, I'll definitely discuss and get back to you on that.
Yeah, I mean, I was just curious. So if it doesn't work, no problem if you can't share it. But is it still possible to submit solutions, or after this meeting it's closed, the submission?
Ayush, can you answer on that? So it should be possible.
Yeah, it is possible to submit.
Okay, yeah, thank you.
I believe you can make a submission at any point in time. Ayush, would that be correct? Or maybe hasn't told me, but I do believe you can make a submission at any point in time. And in case you are not able to make a submission, you can definitely reach out to us and we can see if something's wrong. But for the most part, you should be able to make a submission at any point.
You can submit for as long as like you want. Yes, can you hear me?
Yes, Ayush,
Yeah,
I can.
okay. Yeah, thank you.
right. And any other questions?
So from my side, no more questions.
Awesome. Then in that case, I'll hand it back to Sneha. So thank you.
Yeah, thanks for that, Nimish. If there are any more questions, we can discuss them now. Otherwise, I'll move on to the new puzzle that has just gone live. So the latest puzzle is about building a self-checkout. So I'm assuming we all know about the Amazon Go stores where you just pick up whatever you want and then you leave, and you're charged for those items accordingly. This is a slightly different version of it where you have certain food items on a conveyor belt at a supermarket, and you're given a video of items on the conveyor belt. And what you have to do is, with one set of input, the video input, you have to detect all the unique items on the belt, count their quantities, and calculate the final bill amount. So it's a bit of a challenging problem, but it's also a very interesting problem. And basically the input over here is video of a self-checkout conveyor belt, and the output is a bounding box of the relevant classes, the items that you identify, and the final bill. So this puzzle will cover things like stitching frames together and creating one long image from a video, how to use HSV range to identify unique items in image, how to use YOLO V5 to detect unique items and create bounding boxes, and also how to use image contouring to separate items. As for the bill amount, that's a little bit of a tricky thing. You have to figure it out. We have left a hint on the challenge page, so you should be able to figure it out quite so easily. But that's the puzzle. It's a very interesting one. Our team has worked really hard on creating it, so I definitely recommend you check it out. And we'll be sharing a video explainer for this puzzle soon as well, and you'll get an email as soon as it is live. That's it. Thanks a lot. Thank you for joining, and the recording for the session will be available shortly.
Thank you.
Thank you.